Hey, this video is on molecular geometry. I made another one that just showed our shape sheet. This will show a little bit more, but the shape of a molecule is all based on what's called VSEPR. This VSEPR theory right here. So VSEPR stands for valence shell electron pair repulsion theory. Sounds fairly complicated, it's really not. All that means is electrons around the central element in a molecule, it's like this molecule right here. Electrons around the central element want to be as far away from each other as they can because electrons don't like each other. So remember, there's electrons in these bonds. Electrons around those bonds want to be as far away from each other as they possibly can be. So valence shell electron pair repulsion. Let's go through some molecules here. So first thing, there'll be something called electron geometry and molecular geometry. So electron geometry is just where the electrons are at. Electron pairs around the central element. Molecular geometry will be where the atoms are at around the central element. So if we have a central element here with, this would be a shared pair of electrons. Remember, a bond is two electrons and a shared pair of electrons. So we have an atom, no unshared pairs on the central element. So first thing, the bond angle would be 180 degrees. That angle from there to there is 180 degrees. That's as far as those electrons can be. So electrons repel each other. They want to be as far away as they can. Electron geometry, linear. So electron pair over here, they're linear. They're straight across from each other. And molecular geometry is linear. One thing, whenever there are not any unshared pairs in the central element, these two will be the same. Anytime there are some anytime there are some unshared pairs on the central element, these will be different. The molecular geometry and electron geometry will be different when there are lone pairs in the central element. Let's say that we have another thing in there. So now we have central element with electron pair, electron pair, electron pair. Your bond angle is 120, 120, 120. That add up to your 360. That's as far as they can be away from each other. Your electron geometry is trigonal planar. Trigonal meaning there's three elements coming off the central element. Planar meaning they're all the same plane. And your molecular geometry is trigonal planar. So again, whenever there are no unshared pairs around the central element, your molecular geometry and electron geometry will be the same. Let's say that instead of there being a bonded pair here, let's say there was a lone pair. So let's get rid of the bonded pair and put in an unshared pair. So now we have bonded pairs, or a shared pair of electrons in this bond, a shared pair of electrons in this bond, unshared pair up here. So the electron geometry is still electron pair, electron pair, electron pair. Is still trigonal planar. That didn't change. There's still three electron pairs around the central element. Two of them are shared, one's unshared. The molecular geometry is now bent. Okay? And this angle actually would not be quite 120. So there's still repulsion between these electrons and these electrons, between these electrons and these electrons. And unshared pairs always have a little bit more repulsion than shared pairs. So it's usually about 2 degrees difference. This would actually be about 118 degrees here, 2 to 2.5 degrees difference. So just know that this bonding would be a little bit less than 120. You don't have to know exactly what it is, but about a couple degrees less than 120. All right, that's the 3 pairs around the central element. Let's go to 4 pairs around the central element. So let's start with 4 shared pairs. So now we have a central element with 4 shared pairs. Notice your bond angle is not 90 degrees. It's a little bit bigger than 90 degrees. It's 109.5. Okay, you do need to know that. It's 109.5 degree angle. And again, it's 4 shared pairs. So molecular geometry is tetrahedral. Electron geometry, tetrahedral. Tetra meaning 4. So let's replace one of these shared pairs with an unshared pair. So just got rid of one. Let's put a unshared pair on there. See if I can change this shape. Trying to. There we go. So we still have 4 electron pairs around the central element. 1, 2, 3, 4. Whereas before it was just a bonded pair. Here now it's an unshared pair. So electron geometry is still tetrahedral. That won't change. Whenever there's 4 electron pairs around the central element, whether they're shared or unshared, that will still be tetrahedral. Molecular geometry is called trigonal because there's now 3 elements coming off there. Pyramidal because it's in the shape of a pyramid. And remember, this bond angle was 109 between each of these. This is approximately 109.5. But this would now have decreased a little bit Okay, so down here this maybe be about 107 degrees. It's about 2 degrees less again. The other thing could happen here is we could have, let's take away another bonded pair, add in another lone pair. So still 4 electron pairs around the central element. Electron pair, electron pair. Those are unshared pairs. Shared pair, shared pair. So still tetrahedral for electron geometry. Molecule is now bent. And different bent than we had before, just a little bit more bent. So these 2 pairs will make this bond angle be a little bit less down here, about 105 degrees. Again, it's about 2 degrees more per pair than unshared. So whenever there's 4 electron pairs around the central element, it's tetrahedral. It can be tetrahedral for the molecule, could be trigonal pyramidal for the molecule, or could be bent for the molecule. All right, let's go to expanded octet. So when there's more than 4 electrons pairs off the central element, so more than 8 around the central element. Let's get rid of this. Let's start with 5 bonds coming off the central element. Kind of get a look at this 3-dimensionally. Notice now our bond angles are 90 degrees for these. Not as concerned about those. The other bond angles I was worried about, and these are not all 90 actually, just so you know. I'm more concerned about the bond angles on the first ones we did. This is called trigonal bipyramidal. The way I remember that is tri plus bi adds up to 5. 3 plus 2. There's now 5 electron pairs around the central element. Again, expanded octet. So that'd be molecular geometry and electron geometry because there's no unshared pairs. Those are the same when there's no unshared pairs. So let's get rid of a bonded pair and put in a lone pair. Get rid of a bonded pair, put in a lone pair. So we still have 1, 2, 3, 4, 5 electron pairs around the central element. Okay. Shape is called seesaw. Okay, shape called seesaw. Kind of like it kind of looks like a seesaw, almost like going back and forth there. Again, electron geometry is still trigonal bipyramidal. So for all these, it'll be that. Let's get rid of another bonded pair and put in another lone pair. So get rid of another bonded one, put in another lone pair. Okay. Notice it's called trigonal bipyramidal for the shape because these 3 are kind of in their same plane, and then these are above and below there. Molecule, still trigonal bipyramidal for electron. Molecule is T-shaped. Okay, molecule is T-shaped. You can kind of see why it's called T-shaped right there. We can get rid of another bonded pair, lone pair. Now it goes back to linear. Doesn't seem like it would be because you have 2 lone pairs here and only 1 lone pair up on top of here, but it is pretty linear in shape here for the molecule now. So you've got 4 different shapes there. When the electron geometry is trigonal bipyramidal, so when there's 5 electron pairs around the central element, you can have linear, you can have T-shaped, you can have bent. No, that's not right. Sorry. Get back to there. Messed you up, sorry. Now you're back, sorry. So you got trigonal bipyramidal. Get rid of that. Seesaw. Did not mean to do that. T-shaped, and then linear. All right, let's start back over. One more. Now if there can be 6 bonded pairs, so another expanded octet. And this is called octahedral. And the reason it's octahedral is there'd be like a 4-sided figure on top here, like if you put a little triangle between there, a little triangle between here. You'd have 4 triangles on top and 4 triangles on the bottom, so it's called octahedral. So again, expanded octet, there's 12 electrons around the central element. You got 6 pairs. When the molecular geometry and electron geometry are the same, when there's no unshared pairs. So let's run through these real quick. Get rid of a bond, add in a lone pair. Now it's called square pyramidal. Kind of see that these form a square back here. You've got a pyramid up on top. Okay, square pyramidal. Let's get rid of this one and put in another pair. Now it's called square planar, which you can see why. You've got your I can say 5 elements in the same plane, electron pair above and below. Let's get rid of this, go there. And we've got, hang on, and we are back to a T-shaped here. We won't do as much with the expanded octet ones, but kind of a brief run through. Refer to your shape sheet, okay, as you're doing things. So linear, whenever there's 2 pairs around the central element, 3 pairs on the central element is trigonal planar for electron geometry. There's 2 molecular geometries. When there's 4 electron pairs, it's tetrahedral for electron geometry. There are 3 different molecular geometries. Trigonal bipyramidal, when there's 5 electron pairs, 1, 2, 3, 4 different molecular shapes. I don't know how I ended up with T-shaped in that last one, but didn't mean to. And when there's 6 electron pairs around the central element, we'll go with just those 3 shapes. That's it.